Good day and welcome to our second session for week 5 for heat transfer, and today we will be talking about how do we solve our convection problems, given that in the previous session we established the complexity of the variables involved for computing the convective heat transfer coefficient. So today we will be talking about the empirical approach or the experimental method on how to solve for the heat transfer coefficient of convection. So let's begin. Today we will be learning the different dimensionless numbers which are involved in this method, expound on the most useful dimensionless numbers in particular for our applications, and we will introduce the formulas used for the empirical approach to solve for the different convection problems. So dimensionless numbers are dimensionless parameters which have physical interpretations that relate to the condition in the flow, not only in the boundary layers but also for other flow types. In other words, in simpler terms, dimensionless numbers are used in order to establish kind of a criteria. An example of that would be we learned this in our fluid mechanics, our Reynolds number. This Reynolds number became our criteria for our flow type. So depending on which number you will be using, the applications vary. For example, here we have the Biot number. This is the ratio of internal thermal resistance of a solid to the boundary layer thermal resistance. There are different numbers which are all listed here, and they are applied to different applications and different conditions wherein it is needed. But today we will be discussing only 3, because these 3 will be the ones that we will be using, which will revolve around how we will be solving our common convection problems. As we go along in future topics, we may introduce a bit more, but for now we will focus on these 3 alone. So first is the Reynolds number. Reynolds number is, as we've learned in our fluid mechanics, is the ratio of the inertial forces to the viscous forces inside a fluid which is flowing, given by the formula as shown on the screen. So this becomes a criteria to dictate whether the flow type is turbulent, or is it laminar, or is it in the transition phase. The purpose of this number is to establish the characteristics of the flow. Next, we have the Prandtl number. Now, what is the Prandtl number? This is the ratio of the kinematic viscosity over the thermal diffusivity. This number becomes a measure of how effective is the transport of energy via mechanical movement, mechanical diffusion in terms of the velocity, as we can see here, and the diffusion of energy by the thermal boundary layer. So an expression for the Prandtl number can be shown here. This is the boundary layer, the distance to the boundary layer, and this is the thermal boundary layer. Thermal. And this is the Prandtl number raised to the exponent n. This n is varied depending on the type of fluid concerned. So where do we get this Prandtl number? This Prandtl number, we know that computing the boundary layer and computing the thermal boundary layer is not easy. They are difficult to compute, but we already have a tabular form for the Prandtl number, and these are located in your Appendix A, particularly Appendix A.4 all the way up to A.9. Since A.1, 2, and 3 are solids and they do not flow, so the Prandtl number starts at table A.4. A.4 is for your gases at atmospheric pressure. A.5 is for saturated fluids. So number A.6 is for saturated water, especially water, since this is used in almost all applications concerned in mechanical engineering. A.7, we have liquid metals. So these are the different commonly seen fluids that can flow across simple shapes and are very common for our heat transfer applications. So moving on, next number is the Nusselt number. The Nusselt number is the ratio of the convective to the conductive heat transfer. So if we have our Nusselt number, conductive heat transfer can be located back here. As you can see, K is located here. So if we have our Nusselt number and we have our conductive heat transfer, we can simply solve for our convection heat transfer coefficient. The problem now is, where do we find this Nusselt number? So here comes the methodology of the solutions that our previous researchers and experimenters have conducted. So the chapter 6S contains some mathematics, the actual mathematical derivation of how we would solve our convection problems if not for the empirical methods. But the solutions here can be rather complex and lead to very difficult mathematics, which we will not be able to tackle in the short amount of time that we are given. This could perhaps be one of your specialties or your topics in the future should you proceed to a master's degree or research further into the field of heat transfer. But for now, we will be using the empirical method. You can read up the empirical method on 7.1. The purpose of the numbers earlier, the Nusselt number, Reynolds, and Prandtl number, is to be used in our methodology of solution, which will be empirical in nature. In other words, when we say empirical, it is formed via experiment data. So the setup of the most common experiments conducted is, here we have a flat plate. We have air moving across it, above it. These parameters are set, and we have a heater which provides heat to the flat plate, and this heat can be calculated using our simple voltage times current. This will give us an energy flow which will translate into the value of heat. Since we can control the parameters, we know the area, we can measure the surface temperature, and we know the fluid temperature. Therefore, having known all of these different parameters, we can calculate for our H. Now, what they do is they repeat this method for a variety of conditions. They may change the velocity, they may change the length of the plate, and the control fluid being used, they can change any variable that they want to change, which gives us different values of H. Now, after a multiple repetitions of this experiment, they would find a linear behavior, or they would find an expression where the Nusselt number can follow a... This log here shows that the behavior of the numbers here are logarithmic in nature. So if I were to graph this in a arithmetic scale, this would look like a logarithmic curve. But since this is in the log scale, this translates into a linear scale. Now, what they created is an expression of the Nusselt number in relation to a specific constant, the Reynolds number, and the Prandtl number. Because remember, varying these different variables here would change ultimately the variables concerned for the Reynolds number and the Prandtl number. The Reynolds number is dependent on the velocity over the viscosity and the characteristic length, and the length of the plate can be varied, and also the velocity can also be varied. The fluid, however, once changed, the properties of its kinematic viscosity and its thermal diffusivity will change, affecting the Prandtl number. So ultimately, what the experiment is doing is changing the variables and looking at how much these numbers change. So this, in the end, gives us a useful and very convenient expression for us to solve for a specific Nusselt number. And remember, once we solve for the Nusselt number, we can compute for our once we have this Nusselt number right here, solving the convection heat transfer coefficient will be much, much easier. So it is important to note, however, that the assumption lies with constant fluid properties. It is assumed that the fluid properties do not change across the plate, and what we can do there, since we know that there is certainly a variation across the boundary layer, and this may influence the different thermodynamic properties or the different Prandtl numbers and Reynolds number that you may compute. So a workaround across this problem is to use what we call a film temperature. Now this film temperature is just simply your surface temperature and your fluid temperature divided by 2. The average of the surface temperature and the fluid temperature. So when getting the value of your thermodynamic properties, when looking at your appendix, it is best to look for your film temperature, the temperature in between your fluid and your surface temperature when evaluating your Nusselt number. So the general steps in solving problems involving convection is, first, calculate your Nusselt number. And remember, to calculate your Nusselt number, you need your Reynolds number and your Prandtl number first. So your Reynolds number can be calculated. Just find your x, find the velocity, and find the viscosity. As well as we need our Prandtl number, all of which the data can all be found on these few tables right here. So be familiar with the table and you will not have that much difficulty answering convection problems. The next is, once we've established our Reynolds number and our Prandtl number, we will use the correct value for C, use the correct value for M and N. So these are three variables which are dependent to the geometry and the flow condition. So when I say geometry and flow condition, it depends whether it's a flat plate, it's a sphere, it's a cylinder, it's a pipe, or whatever. And the flow condition refers to whether it is laminar, turbulent, or transition. So the topics that we will be tackling will only consider laminar and turbulent. And the third, once this formula has been established, we will use our Nusselt number calculated to find our H using the formula below. Now remember, our formula requires us to know what thermal conductivity K is, and again, our K can be located on our Appendix A, tables 4 to 7. So once we have our K, our L would be given, or we can interpret that from our problem, giving us a value for our H. The next is to apply the H to the correct convection equation and evaluate our condition. So it's as simple as that, and complexities here could be found if there would be multiple sources of heat transfer. For example, there would be conduction involved and radiation involved, which will ultimately affect what the convection equation will be, because we need to, of course, look at our thermal circuit. But aside from that, if we manage to master the procedure in getting our Nusselt number and getting our convection coefficient, this topic of convection would be relatively easier if we know how to conduct these first steps